Hello and welcome. Now, today my topic of discussion is Planck's radiation law. Now, this law was given by Max Planck in 1900 to explain the distribution of energy among different wavelengths of a black body radiation. Max Planck, he introduced entirely a different concept. He said that the cavity walls of the black body, they are made up of atoms, and each atom is an oscillator and emits electromagnetic energy into the space of the cavity and also absorbing the same radiation from it and maintaining thermal equilibrium. He introduced a revolutionary idea that energy of these harmonic oscillators is number one, En is equal to nh nu, where n is quantum number, h is a Planck's constant, nu is the frequency of the oscillator, and n takes the values 1, 2, 3, 4. And when you apply these values, you will come that energy of these oscillators is h nu, 2h nu, 3h nu, 4h nu. That means we do not have values in between h nu and 2h nu, and between 2h nu and 3h nu, or between 3h nu and 4h nu. This means that the value of energy is discrete. In other words, we say the energy of these harmonic oscillators is quantized. And his second assumption was that the oscillators do not emit or absorb energy continuously, but only in jumps. That is, an oscillator emits or absorbs packets of energy. Each packet carrying an energy h nu, and that can be given by this relation del E is equal to del M into h nu. Now, with the help of these two assumptions, he developed a theory which explained the whole black body spectrum, and also it became the basis for development of quantum mechanics. Now, let us now calculate the average energy of Planck's oscillator of frequency nu. The relative probability that an oscillator has the energy h nu at a temperature T is given by the Boltzmann's factor e raised power minus h nu by kt. Now, if this equation can be written in a full form, nr is equal to n0 e raised power minus r h nu by kt. Now, if we have n0, n1, n2, and n3 at number of oscillators with energy. This is zero energy, with h nu energy, with 2 h nu energy, with 3 h nu energy. The total number of these atoms can be written as n is equal to n0, n1, n2, n3, n4, and so on. Then you substitute here the Boltzmann's factor for n0. It will remain as n0, and n1 you can take as r is equal to 1. Then for n is equal to 2, r is equal to 2. And then for r is equal to 3, you will get n3. And then you will write down the equation like this. And from this, you will take h nu by kt is equal to x. And you will have this exponential series 1 plus e raised power x plus e raised power 2x plus so on. And this can be written as 1 by 1 minus e raised power x. And therefore, this n becomes n0 1 by 1 minus e raised power minus h nu by kt. This is equation first we call. Now we find the total energy of these harmonic oscillators. Now total energy can be written as the energy of all these atoms n0, n1, n2, n3. Now we write down E is equal to 0 n0 plus h nu n1. Now h nu is the energy of each of n1 atoms, and 2h nu multiplied by n2 plus 3h nu multiplied by n3. Now here you can clear this concept that we have for n3 atoms, each n3 atoms has 3h new energy. Therefore, we move forward and we take h nu n0 e raised power minus h nu by kt constant, and inside you will get this equation again. You take minus h nu by kt as x, e raised power minus h nu by kt as x, and you will have this expansion, and which you can use 1 by 1 minus x whole square, and then finally you will find the energy of total energy of these harmonic oscillators. It is given by this equation, equation 2 we call. Now we find the average energy of these harmonic oscillators. We take the total energy divided by the total number of atoms, and this equation becomes like this, and finally we arrive at this equation. uh, uh, we get this equation, uh, E bar is equal to h nu by e raised power h nu by kt minus 1. This is the final equation for average energy of the harmonic oscillator. Now we move ahead. We now can say that in the cavity of the black body you have electromagnetic radiations. Now these radiations are moving in all possible directions, and they get reflected from the walls, and when they come back they form standing waves. Therefore, there are standing waves inside the cavity of the black body. Now, we have to count these all these standing waves, and we find the number of modes of these standing waves having frequency between nu and nu plus d nu per unit volume, and this equation becomes 8 pi nu square by cq d nu. Now, therefore, we have the total number of standing waves or the modes in the cavity, and each this energy, average energy of this harmonic oscillator or these waves is given by this. And if you multiply these two equations, it gives the energy density of the black body radiation in the frequency range of nu and nu plus d nu. And when we multiply this, we'll find this e nu d nu is equal to 8 pi nu q by cq into 1 by e raised power h nu by kt minus 1, and this is with respect to d nu. This equation is the Planck's radiation law in terms of frequency. Now, before we move to other video for more discussions, I will show you that how we have calculated this number of these modes of standing waves having frequency between nu and nu plus d nu per unit volume, that is 8 pi nu square by c cube, how we have obtained. Now we know in classical physics we have second order differential equation for waves in a linear form. It's given by this in one dimension. So we can write down that equation in this form, and you can also write down this equation in 3 dimensions. Now, the solution of this equation we write in terms of standing waves, standing wave equation. The standing wave equation is u of xt into a sine of n pi x by l into cos of 2 pi nu t. Now, this is the solution. We can write down this as solution of this second order wave equation. Now, we differentiate it twice, and with respect to x, and then with respect to time, and substitute in this equation, we find the square of this quantum number, this equation, this very important equation. Now, coming to the other side, if we have got a one-dimensional box of length L, and in this length we have this standing waves are formed, and these standing waves, you know that these standing waves have got this on the walls of this one-dimensional box. I know these nodes will be formed. Nodes means the particles of will be completely at rest, And now the length L of this one-dimensional box can be written as this is integral multiple of half the wavelength, because this is a half wavelength, and uh, half wave, all the if we count the waves, it will always be half the wavelengths, and we have taken integral multiple of this. Then we use C is equal to nu lambda. We know this equation, and from these equations you will find dn is equal to 2L by C into d nu. This is one more very important equation which we are using here below. And now we take the cavity, black body cavity, as a space which is filled with these standing waves, and we take its radius as n, uh, and then we calculate, we take a small thickness of that volume dn, and multiply it by the surface area of the sphere. Then we find the volume of the sphere, which contains these standing waves having frequency between nu and nu plus d nu. That means this whole sphere is made up of these waves, these standing waves actually. And we can calculate the number of these waves, 4n square, 4 pi n square dm. And you use this value of dn here, and we'll get this relation. And now here we can take the sphere's octet part, or 1 by 8th part of this sphere, where we have positive values. And since we are interested to deal with these positive values, we multiply this equation by 1 by 8th, and then we multiply this equation again by 2, factor 2. This factor 2 is important because there are two types of photons. One are the left polarized photons, other are the right polarized photons. We multiply this equation by 2, and we get this final equation 8 by nu square by c cube. And therefore this equation 8 pi nu square by c cube d nu, it represents the number of standing waves having frequency between nu and nu plus d nu per unit volume. And we use it in the black body radiation. Now, for further discussions, we'll move to another video.